For instance, let's think of the length of a vector. If I talk to you about the length of a segment, you know what I mean, right? And in fact, if we are in two dimensions, then given a vector v1, v2, I can put it at the origin. I can put its tail at the origin and sort of use a standard kind of representation. And then, of course, the height of this segment can be drawn separately, in which case v1 is the horizontal component, v2 is the vertical component, and we know from the Pythagorean theorem that the length of this segment is going to be given by the square root of v1 squared plus v2 squared. Well, that is familiar. That is, the right-hand side is familiar. What's that thing on the left-hand side? Well, that's the symbol that we're going to use to denote the length of a vector. Once again, you may wonder why we're introducing a different symbol when we could just call it the length of the vector or something like that. But the reason is that this length will then become something much more abstract that we'll be able to apply in other situations. Now notice something quite interesting. If we go to 3D and if we look at a three-dimensional vector v1, v2, v3, and we draw its vertical component v3, and then from its projection on the xy plane we look at the horizontal component v1 and the v2 component along the y-axis. Now, if I draw the diagonal of that rectangle that I just formed on the xy plane, should not be difficult. In fact, it should be very easy for you to use that diagonal to prove that the length of this vector v in 3 dimensions is actually given by a formula very similar to the one in 2 dimensions. So it's in fact given by the square root of v1 squared plus v2 squared plus v3 squared. This is sort of a generalized Pythagorean theorem. Well, we're going to use this commonality between 2D and 3D to define later on the length of a vector more generally in situations which are not visual, which are not geometric, and even in situations where there is no segment, there is no components, and vectors will be something much more abstract. So start looking at this thing again, starting from the visual, from the geometric that you're familiar with, but then moving on to the abstract and to the key properties. So notice how the length of a vector both in 2D and 3D is defined as the square root of the sum of the squares of the components. Now, one little thing here which we're going to see again later. A unit vector is a vector of length 1. So if that length that we've just computed ends up being 1, for obvious reason we're going to call it the unit vector. Why bother, you say? Well, we're going to see shortly why that is an important piece of information. Let's look at another characteristic, another feature of geometric vectors, and it is the issue of the direction. Remember, when we start talking about vectors, and perhaps when we start seeing vectors in your high school, you were told that a vector is something which has a magnitude, which so far we've called still the length. We're going to call it a magnitude soon, and a direction. So how are we going to define the direction of a vector? Well, if we're in 2D, that's easy. All we need to do is give the slope, right? So the slope m of that vector is simply going to be given by the rise over the run, so that's v2 over v1. So far, so good. Well, maybe we're still that slope still does not tell us which way the directed segment actually goes, whether it's from the left to the right or from the right to the left. So in other words, just that slope by itself doesn't tell us which one is the tip and which one is the tail of the vector. But that's already a pretty good idea. But look at what happens in 3 dimensions. Well, in 3 dimensions, of course, we'll need the same kind of slope. We need to find out how that vector is inclined along the xy plane. But that's not enough. We also need to know how much that vector v is inclined vertically towards the z-axis. So we need a second slope. Right? How are we going to compute that second slope? Well, I'm going to leave it to you again as a little geometrical exercise to refresh your memory on geometric facts about the fact that this m2 is going to be given by v3 divided by plus or minus the square root of v1 squared plus v2 squared. Again, I'll kind of leave that to you, the task of checking that sort of geometrically using again definition of rise and run, but I'm not going to tell you anything else about it. What I really want to point out to you is the fact that now, even just in 3 dimensions, this direction thing is becoming a very complicated, a little bit of a complicated issue. It requires 2 numbers. One of them will have to also decide whether it's positive or negative. And just imagine what's going to happen when we try to extend this thing into higher dimension, just to complicate it. So we're going to need a better way of defining the direction of a vector. So again, use this one, this visual one, this familiar one as a starting point, but we're going to need something a little bit better, which is coming soon.